Good morning. Our topic today in physics is friction and inclines. So let's start by taking a look at the box on the surface there. It has a velocity vector to the right, and we have a zoomed in close-up of the surfaces between the table and the box. And it turns out even the most smooth surfaces are really quite rough. And that generates something that we know to be as friction. And there's a couple types of friction that we'll talk about today, starting with something called kinetic friction. And before we get into that, we want to realize that friction is something that we try to reduce a lot of times to increase efficiency. However, friction is a good thing because without it, we wouldn't really be able to move anything horizontally on planet Earth. If you think about trying to open a door, the friction between the floor and your shoes allows you to pull the door open. So it's one of those things that we need it, but in some cases we try to reduce it. So for kinetic friction, the equation is here. The force due to friction is equal to the coefficient of kinetic friction multiplied by the normal force. So let's talk about the normal force first. The normal force in this case is going to be equal to the weight of the box, and that's basically the measurement of how the pressure between the two surfaces. If you take your hands right now and push them together, the harder you push, the harder it is to try to slide your hands back and forth. So what you're doing is you're generating some normal forces to increase the friction. And we see this a lot of times, like putting weight in the back of a pickup truck to increase the normal force and therefore increase the friction between the tires and the road. So there's some real life common sense applications for this stuff. The coefficient is a measurement of the surface roughness, essentially. So you can have a coefficient with sandpaper, for example, where it'd be a really large coefficient. Or if you were, let's say, with ice skates on ice, your coefficient would be very small. And we'll look at a table of some coefficients here in just a moment. But essentially, all you do is you multiply the coefficient of kinetic friction times the normal force, and that's going to give you a frictional force. So here's some coefficients. We've got wood on wood, 0.4 and 0.2. So we have two columns here. The first column represents the coefficient of static friction, and the second column represents the coefficient of kinetic friction. So static friction is when the objects are not sliding. So think about kinetic friction as this is the same thing as sliding friction. So it turns out there's sort of a bit more friction when at the moment before we start slipping, and then friction is reduced significantly. So that's why you don't want to spin the wheels on your truck or car to try to get unstuck. The more you spin the wheels, your friction is actually being reduced. You want to rock the car back and forth and try to not have those wheels start to spin, and your coefficient of static friction is going to be a lot more than it is with the kinetic friction where it drops. So some other surfaces, just to give you a sense of these values, on the really, really small end synovial joints in human limbs have just this amazing low coefficient of friction. Human body physics is pretty cool stuff to study. Teflon, rubber on wet concrete, we would expect that to be pretty high, and even higher if the concrete is dry. So here's your driving on dry roads versus slip wet roads. It is reduced when the pavement is wet, but a coefficient of 1 is about as big as you will see, and the coefficient of 0.01 is about as small as you'll ever see. And you'll notice that the coefficient doesn't have any units associated with it. So we're multiplying this value by a force already, the normal force. And so our answer is just going to be a force in newtons, which will be the frictional force. So with static friction, this is that frictional force between two surfaces that are not moving. So typically what we'll do is we'll take objects and we'll elevate them on an incline. And if they're not sliding down the incline, well, it's static friction that's holding the object in position. And our experiment this week is going to involve something exactly like that. And we'll be able to figure out the frictional force involved by measuring some angles. And an interesting thing that static friction does is, instead of seeing an equal sign, we see an inequality, a less than or equal to sign, meaning that static friction, sort of like the normal force, has the ability to fluctuate. So what that means is, if there's no force that's pushing horizontally, let's say it's a box sitting on a table, well, the static friction is zero. Now as I begin to apply a horizontal force to start pushing this box, there's a fair bit of force there before I get it to start moving. So as I'm pushing, static friction will increase to match my pushing force until I reach the point at which I exceed the maximum static friction, and then the object starts to slide, and at that point I'll switch over to using kinetic friction. And so to explain that a little further, we have a graph here to understand what's happening. So on the x-axis here I have an applied force. So let's stay with this example of a box sitting on a table. My applied force is some horizontal force I'm pushing with, and if the force that I apply is zero, well, there's no friction force at all. It's just the object's weight and the object's normal force, which should balance out to have a net force of zero. So as I begin applying a force here, I'm pushing, increasing all the way to just below 40 newtons, what we see is the static friction force responding in a linear fashion. And so it's going to stay there until you push hard enough to get the thing to slide. And when you hit that point, all of a sudden, friction's going to drop off significantly, and we're going to switch over to using kinetic friction. And this is going to be a value less than static friction because, as we saw from this previous slide, the coefficient of static friction is more, almost twice as much as the coefficient of kinetic friction. So basically, I have less friction when I'm sliding versus remaining stationary. And we use the new lower coefficient, multiplying it by the normal force again, to now determine the force due to kinetic friction. And what this would represent here, as we continue to increase the normal force, is that whatever that kinetic friction force is, it's going to remain relatively constant as the object is sliding. You can see some small fluctuations here, but in general, you know, this kinetic friction force is going to be only based upon the magnitude of the normal force and the magnitude of the coefficient. It doesn't really have much to do with the speed that the object is going at. If I'm going at 5 miles an hour versus 10 miles an hour, the kinetic friction force is going to be roughly the same because it only depends on that coefficient and that normal force. So that's a really important point to wrap your head around. Then what we start to do is we start putting blocks on inclines. And if we look at this situation, this is why we don't use the weight force to determine the friction. We have that normal force in the equation, not the weight. And you'll see the reason for that with this example here. So this object sliding down the incline has three forces acting. Oops. Normal force, gravity, and frictional force. And let's say that this object is at rest right now. If that's the case, the friction force is opposing gravity. You might be wondering, how does that work? The ramp is sliding this way. Gravity, I've taught you, always points straight down. We kind of need to take gravity and resolve that vector into components so that one of the components is going to be parallel to the surface and one of them is going to be perpendicular to the surface. So part of the object's weight is actually going straight perpendicular, not straight down, but down this direction into the ramp, and part of the weight is wanting to pull it down the ramp. And so in a second video I'm going to make for you, I'm going to show you how to do that, and that allows us to examine the forces so that they're all pointing along the same plane, either straight up, straight down, or left or right, and imagining that we're not on a ramp at all. So hopefully it'll make it easier to deal with. So I guess that's it for now. Yeah. Have a good day.